In America, one barrel of crude oil can quietly turn into $400 gasoline, $300 diesel, and $200 clothing and plastics, yet most Americans never think about it. So what happens in between? First, the crude oil goes into a towering steel column and gets heated to extreme temperatures. Inside, the heat isn't even. From bottom to top, the temperature drops by more than 540 degrees Fahrenheit. That gap is the key. Each component boils at a different point. The lightest materials rise first. At the top, petroleum gas is collected, the same fuel many homes use every day. Just below that comes gasoline, the most valuable product, even though it makes up only about 1/5 of the barrel. Lower down is naphtha, the source of plastics and synthetic fibers used in modern clothing. Next comes diesel, the backbone of trucks, factories, and heavy machinery. Near the bottom sits heavy fuel oil, thick and dirty, but incredibly powerful, which is why giant cargo ships rely on it. At the very bottom, what's left becomes asphalt, holding together roads and highways. Now you understand just how valuable crude oil really is. Can you believe this? This tool draws perfect circles on steel pipes like it's sketching on paper. It's a round hole marker, one of the most precise ways to lay out circles on curved metal. At first glance, it looks too simple, but the accuracy comes from how the whole setup locks itself in place. The base is shaped to sit securely on round surfaces like pipes and curved steel, so it doesn't rock or drift while you're working. Inside, the base is a strong magnet with an on and off switch, and it does more than just hold the tool down. It keeps everything completely frozen in position. Now look at the arm. What sets it apart is the 180-degree rotating dial with built-in levels, which lets you fine-tune the angle and dial in the exact center axis. The real advantage here is control, not speed. Once everything lines up, the marker traces a perfect circle around the pipe, evenly spaced and perfectly balanced. No eyeballing, no guessing, no crooked lines you only notice after the cut. And it doesn't stop at pipes. Angle iron, I-beams, odd-shaped steel, anywhere a straight ruler fails, this still works. So the real question is, what's actually more precise than this? Why would a ship flood its own deck in the open ocean? It's not an accident, and it's not sinking. You're looking at one of the most capable industrial vessels ever built, a semi-submersible heavy lift ship in action. At first, everything looks wrong. Alarms are going off. Seawater is rushing across the deck. A massive steel ship appears to be sinking itself on purpose. So why do this? Because the cargo it's about to carry weighs tens of thousands of tons. Oil platforms, entire ships. Loads so heavy that even the world's largest cranes would struggle to lift them. Instead of fighting gravity, this ship lets physics do the work. Seawater valves open, flooding massive ballast tanks and causing the ship to sink slowly and evenly under full control. The deck drops below the surface, turning the ocean into a loading dock. Tugboats slide the cargo into position. The water is pumped back out, and the ship rises again, lifting the load like a steel giant carrying another giant out of the sea. It may look chaotic, but every second is carefully calculated. So here's the real question. Is this the wildest loading method humans have ever engineered? Can you believe this? If firefighters cut corners on this step, the next fire could turn it into a death trap. Don't let appearances fool you. A hose pulled straight from a fire scene isn't just wet. It's coated with ash, toxic chemicals, carcinogens, and combustion residue. On the outside, it looks harmless. But inside, trapped moisture creates the perfect environment for mold and bacteria to thrive. And it gets worse. Even a tiny grain of sand, something you'd never notice, can become deadly under extreme pressure, causing a hose to rupture at the exact moment it's needed most. That's why when firefighters leave a scene, they don't rest first. They clean. Every hose goes through a full, deep clean process. High-pressure water strips away contaminants. Then it's fed into massive machines that scrub it aggressively. After that, it's sent into drying cabinets for a full heat cycle, inside and out. Not for looks, not for cleanliness, but for survival. Only when it's completely clean and bone dry does it get rolled back onto the truck. Because every clean inch of hose is an invisible lifeline the next time they charge into the flames. When they respond to the next fire, could this be what saves a life? America pours more concrete into foundations than almost any country, yet many buildings don't actually require it. So how does that work? Across Europe and North America, builders use driven foundations instead, setting wooden posts into steel brackets anchored straight into the ground. Each bracket includes a steel stake driven deep into the soil. This isn't just something holding it in place, it's where the strength actually comes from. Not from weight, but from friction and soil resistance. Once the stake is in, the wooden post drops into the bracket. The bracket brings the column perfectly vertical and locks it in place. This isn't a workaround or a shortcut, it's built this way on purpose. It's designed to meet load and code requirements when installed correctly. Foundation and wall support form at the same time. No curing, no waiting. That speed is exactly why it's common on farms, job sites, and remote builds. That's why barns, workshops, and light industrial buildings across the American are built this way. No concrete doesn't mean no foundation. It just means a different one. So would this actually pass inspection in America? Why is Japan considered the ceiling of global industrial manufacturing? Watch how this engine connecting rod is forged, and you'll understand. The process begins with the die itself, where a massive block of high-grade tool steel weighing nearly 2 tons is positioned on a precision machining platform, carefully aligned and milled using specialized cutting tools until a complete forging die is produced with extremely tight tolerances. At the same time, the raw material for the part is prepared, as a solid steel billet is cut to size and transferred to the forging area, where it is heated until the metal becomes fully malleable. The glowing billet is then pre-shaped under initial hammering to establish its basic geometry, before being reheated and placed into the finished die. An 8-ton forging hammer begins striking repeatedly, and with each impact, gradually forming the final geometry of the connecting rod. Once forging is complete, excess material around the edges is trimmed away and the surface is finished. And just like that, a forged engine connecting rod is complete. After forging and finishing, this single component is expected to withstand millions of load cycles inside an operating engine. Would you trust a part like this inside your engine? Welcome to the most advanced production hub on Earth for heavy machinery tracks. What looks like simple steel links here is what keeps massive machines moving under extreme weight. So how does it actually work? It begins with individual steel links and pins, each precisely machined and heat-treated to survive constant impact and heavy loads. These links are aligned and pressed into long sections, then coiled simply because handling something this heavy in a straight line isn't practical. Before final assembly, entire sections are lowered into oil baths, not for cleaning, but because every joint needs lubrication, since dry metal under this kind of load wouldn't last long. The links are then pressed, tightened, and adjusted again, making sure each joint is strong enough to hold while still flexible enough to move. That balance is the key. Track chains don't rely on brute strength alone. They spread weight across dozens of contact points, allowing massive machines to stay stable on mud, rocks, and uneven ground. Once complete, the chain is lifted as a single unit paired with wheels and rollers and checked under load. What looks like a simple metal loop is actually a carefully tuned system where every link matters. This is one of the most precise ways to shape the inside of a gear. That metal tool shaped like a spiked club moves through the bore, but nothing is being damaged. The circular marks forming inside aren't dense at all. Material is being removed gradually, one layer at a time. The method is called broaching. Instead of spinning like most machining operations, the cutter gets pulled straight through under tightly controlled force. Precision comes from the cutter itself. A broach is long, with rows of cutting teeth arranged in sequence, each one slightly taller than the last. Each tooth takes only a tiny bite, keeping the cut stable while the final dimensions slowly come together. Constant contact with the metal builds friction and heat, so coolant has to flow non-stop to manage temperature, reduce resistance, and carry chips away. It may look slow and aggressive, but that controlled pace is exactly why it works. In a single pass, the internal profile reaches full accuracy. Still think this is brute force machining? Do you know how containers are landed so precisely? Workers lift containers weighing tens of tons from a height of about 165 feet, with an error margin of less than 2 inches. The difficulty is comparable to performing surgery. So how do they do it? First, the operator must align all 4 locking pins of the container. Sitting on the crane's control bridge 165 feet above the ground, the driver uses only their eyes and hands watching the container below while controlling 2 joysticks. The left hand moves it forward and backward, the right hand controls lifting and rotation, and the feet adjust. The fine movements with pedals. Every motion must coordinate like precision gears. A beginner might struggle for hours, but a master can instantly sense the tension in the cables and predict how the wind will affect the container. Every eye, hand, and foot movement must be perfectly synchronized. Even more terrifying, workers are usually nearby, and if a container weighing tens of tons falls, it can cause serious injuries or fatalities. So next time you see a crane in operation, would you dare stand close? Why do brand new homes in America always seem to have lush green lawns the day they're handed over? It's not because the grass grew naturally, it's because of hydroseeding. This method is super common in the U.S. Instead of waiting weeks or months for grass to grow, developers spray it on in one go, so the yard looks instantly neat and beautiful. They mix grass seed, wood fiber, fertilizer, water, and a special adhesive into a thick green slurry. Then workers use high-pressure sprayers to cover the soil evenly. The fibers act like a net to hold the seeds in place, while locking in water and nutrients, helping the seeds sprout quickly. The results are amazing, several times faster than traditional seeding and much cheaper too. In just a few weeks, a bare dirt yard turns into a carpet of green. So that lawn you see at a new house isn't a gift from nature, it's a shortcut from technology. If you were redoing your own yard, would you want a hydro-seeded instant lawn? Why aren't big bridges poured all at once, and why leave visible gaps? Those gaps have a name: expansion joints. A bridge lives outdoors and faces big seasonal temperature swings. Between summer and winter, the change can be over 90 degrees. On a deck, roughly 164 feet long, thermal expansion and contraction can add up to around 1 inch. Without joints, the deck could crack or buckle. Building in segments naturally creates expansion joints so the bridge can move freely and avoid damage. Bonus, a segmented layout lets engineers add dampers or isolators at the joints, so during an earthquake or heavy impact, the forces spread out and the structure rides it out better. Worried that piecemeal means weak? Don't be. Each segment ties together with rebar, mechanical keys, and post-tension cables, locking everything into a very strong whole. Smart segmentation balances strength, durability, and safety. What other hidden bridge details surprise you? Why is the nose on some jet engines soft? That nose-like part is the spinner or nose cone. At high altitude, moisture can freeze on the front face. If chunks break off and get swallowed, they can hit blades like bullets. To cut the risk, some lower-speed jets use flexible composite spinners. When a thin frost starts to form, the cone flexes slightly with airflow and vibration and shakes the ice off early. If tiny ice chips do get inhaled, the engine's hot airstream usually melts and evaporates them before damage happens. Most other aircraft use rigid nose cones that can't shed ice by flexing, so they rely on electric anti-ice, chemical de-ice, fluid, or pneumatic boots to handle icing conditions. In short, some jets shake ice away, while many props and other designs lean on heat, chemicals, or pressure. The methods differ, but the goal is the same: keep the airplanes safe at altitude. What other design tricks on airplanes have surprised you? If someone offered you $200,000 a year, would you work on an offshore oil rig? The pay sounds great, but the trade-offs are real. In the Gulf of Mexico, an entry-level roustabout earns around $70,000, often working 2 weeks on and resting 3. After a few years, 6 figures comes fast. Crews who erect derricks can make about $18,000 a month, and platform managers can easily clear $200,000 a year. Why so high? Because the job is seriously risky. You're on slick, oily decks around heavy machinery, and in bad weather, roaring wind and waves can sweep someone overboard. Drilling mud often contains chemicals, and long exposure isn't great for your body. The worst danger is the unexpected. A single mistake or extreme weather can trigger a blowout, a fire, even a full platform loss. So that big paycheck isn't easy money. It's compensation for living with risk and stress far from shore. If the offer were real, would you take the deal and head offshore? That steel mesh wrapped around a brake hose, just how important is it? It's not decoration. Step into the workshop and you'll see a high-speed braiding machine sends hundreds of spools racing along S-shaped tracks, 2 groups moving opposite but interlaced, weaving steel into a tight, flexible sleeve. This braided layer acts like invisible rebar. It grips the inner tube, prevents it from swelling, and spreads pressure across thousands of crossing points. Why does that matter? Because these hoses don't just carry still water, they're built for fuel lines, brake lines, shower hoses, and gas hoses always handling high pressure, pulsing flow, and sudden temperature swings. A plain rubber tube alone would burst. With the steel braid, pressure resistance multiplies, explosions are prevented, and service life is far longer. The mesh also shields against abrasion, sharp bends, cuts, even some chemical corrosion. So what looks like extra clothing is really a muzzle for pressure and a safeguard for safety. Did this clear up a question you've had for years? Why are ships often launched sideways? Aren't they afraid of tipping over? At shipyards, it's routine to see a new vessel slide off the slipway and hit the water broadside. This method is called a side slip launch. When the yard is narrow or the berth isn't long enough, sliding sideways keeps forces balanced and reduces deformation or damage. But that's not the only method. End launching, where the bow slides in first, is also common, but it demands wide, deep water and precise calculations, or the ship could tilt dangerously. Then there's airbag launching. Workers line inflatable polymer rollers under the hull and pump them up, letting the vessel roll into the sea. It's flexible and doesn't require heavy modification, but it needs smooth ground and careful coordination. The most stable of all is floating dock launching. The ship is built inside a dock, water is pumped in, and the vessel simply floats free. Almost no risk, but the cost is extremely high. Each method reflects trade-offs, site conditions, vessel size, budget, schedule, and safety. Have you heard of other launch methods? 2 tons per second enough to fill an entire ship in just 2 days. How is that even possible? The answer is the massive ship loader at the port. From the stockyard, coal travels on conveyors in a relay until it pours out like a black waterfall. A telescopic chute lines up with the cargo hold, spreading the coal evenly. The pace is staggering, 7,500 short tons every hour. If you swapped it for trucks, that's about 250 loads each hour. And what about unloading? That's where the bucket chain unloader comes in. A giant chain lined with buckets scoops coal steadily from the hold, moving up to 3,000 tons per hour. But in many ports, the most common sight is the grab bucket unloader. Each grab can lift about 30 tons, and with a skilled operator keeping the rhythm tight, it can still reach 2,000 tons an hour or more. What looks like brute force is actually precision work balancing flow, suppressing dust, and monitoring safety every second. Which coal loading method do you think is more efficient?